Okay, so we continue on the modulation. Okay, uh, we have gone through this. Okay, it's better just to go to the exercise for easy understanding. Okay, so now we go to the exercise directly. Okay, example. Okay. Example 2.1. An AM modulated signal is generated using signal VT 3 cos 2 pi times 10 to the power of 3. Modulating the carrier signal VC equals to 10 times cos 2 pi 10 to the power 6. So by here we know this one is 10 to the power 3 and this one is 10 to the power 6. Even though it didn't mention this one is VM or VC. They say it's just mentioned V1 and this one V2. So you should be able to tell us, you should be able to guess V1 V modulating signal is 10 to the power of 3, the information signal, because it's supposed to be lesser than our carrier. Okay, so this is for the sake of exercise, so it's mentioned VC, okay, but it can mention V2. Okay, determine the modulation index. So this one is quite straightforward. 3 divide by 10, so you get the modulation index EM over EC. Okay, so that's why you EM over EC 3 over 10. So that's why you get this answer. Okay, and then the upper side band and lower side band and bandwidth. So this one, you need determine the upper side band, lower side. Okay, upper side band, lower side band, and bandwidth. Okay, so upper side band, lower side band, and the bandwidth. So you need to do the omega m, omega c. Okay, so upper side band. Okay, upper side band is omega m plus omega c. Lower side band is omega m minus omega c. Okay, let's say we have point A. This is at point A, and then you have B, upper side band, and then in the middle is your carrier C, FC. Okay, so bandwidth is upper side band minus lower side band. So if you see upper side band minus lower side band, so if you notice omega m plus omega c minus omega m, sorry, omega c. Ni lah, bulan puasa ni dah tersasul. Sorry, bulan puasa ni lain macam. Omega c minus omega m, omega c plus omega m. Okay, so this one is omega c minus omega m. This one omega c minus omega m. So upper side band, lower side band for us to get the bandwidth. Okay, so upper side band is omega c plus omega m minus lower side band omega c minus omega m. So because this one is minus and minus, so cancel out omega c, so you have 2 omega m. Okay, omega m plus omega m. Double side bands, full carrier, so the bandwidth is actually equivalent to 2 omega m. Okay, and then the ratio between sideband and carrier amplitude, the ratio between sideband, okay, so this one is easy just now. M from here just now. Okay, M equals to EC over 2. Okay, and carrier amplitude over EC. Okay, so this is how you get them. Okay, and then you just put the value because you have M is, you already know M is equals to 0.3. Okay, EC, you know EC is equals to 10, and then over 2 and over EC again. So this why you get this. So ratio is 0.15. The maximum and minimum peak-to-peak voltage of the modulating signal. So maximum peak-to-peak. So for it to be maximum, 2 EC plus EM. So you get 26 volt. And minimum peak-to-peak voltage, EC minus EM. Okay. Again, this one is voltage, the amplitude. Okay. Is having shown here. This one, EC. Nampak tak kat sini? This one is EC. Bawah tu negative EC lah. Okay. Sebab tu dia darab dua. Sebab dia ada dua side. Okay. You have the positive part and you have the negative part. So that's why is you have two parts. Okay. That's why you have the two here. Okay. EC plus EM equals to 26 volt and EC minus EM equals to 14 volt. The next is AM modulated signal. What is the envelope equation? What is the message signal? What is modulation percentage? What is the spectrum? So envelope equation is VAM equals to EC plus VM cos omega CT. Okay, this VM is actually EM cos omega M T. Okay, so overall this is envelope equation. Okay, so this question they are not factorized yet. Okay, uh, because they want us to find what is the envelope. And then what is the message signal? Okay, message signal is easy, is omega M. And then modulation percentage, M, EM over EC. This one is in terms of percentage. You get in terms of ratio. Okay, spectrum of the modulated signal. Okay, so now I open the answer. Okay, ini saya buang this merah. Okay. So this is the answer you say where you need to factorize. Okay, you need to factorize just now dia bagi panjang kan. So you just need to factorize whatever inside here. This one is the envelope equation. Okay, EC plus VM cos omega CT. So EC is the amplitude of the carrier 500. This one. Okay, and then where the carrier signal before modulation is equal to this one. Okay, oh dia dah bagi sisi tepi ni terjauh sikit sorry. So this is your envelope equation. After that, message signal. Message signal, since this is EM and since this one is VM, so directly this one is your message signals. VM. And then modulation percentage is easy, is a ratio. So ratio EM over EC. EM you get 200 divide by EC 500. So you get 2 over 5 and times with 100 to get percentage. So it's 40%. And then spectrum of the modulated signal. So make sure when you answering later, please label properly. This one is FM or hertz or kilohertz, whatever depend. Okay. So this is how it is of your spectrum. This is spectrum. Spectrum is frequency domain. Waveform is time domain. So 100 you get from result of M EC over 2. Okay, M you get just now berapa M tadi? 0.4. Okay, saya ambil sini je tadi. Okay, 0.4 EC is you get 500 over 2 lah. Okay, so you should be able you should be able to get 100. Okay, Yes, the peak to peak amplitude. Okay, this one I just open and you try to solve them. Okay. Kejap Okay, you can take it and as an example to you or exercise at home because kalau saya nak pergi satu-satu nanti tak sempat pula pukul 4:30. Panjang ni. Okay. So okay, you can take this photo. Okay, if you want. This is the answer for that. Okay. You can
Doktor,
yes.
tak ada slide doktor?
Huh?
Doktor ada slide ke? Tak ada slide, saya tak nampak apa-apa.
Saya tak share slide
Haa.
Eh,
The
yang lain
slide
diam
dia
je.
exit.
Yang lain
Tadi
diam je.
tadi ada doktor, ni baru.
Tadi ada, lepas tu dia macam left.
Oh,
Keluar.
okay. So, okay. So, nampak So, this one you
Nampak doktor?
letak dekat you punya PDF lah. Boleh masukkan gambar dalam PDF kan? Okay. So, you try first. This one you take photo. Make it as your exercise. Okay. Okay, saya pergi to the next page. Okay. This is
Doktor,
the
answer untuk 3-4 Roman doktor?
3, 4.
Oh, okey, ni.
Oh, 3, 4 sebelah.
Okey.
Hmm.
Sorry doktor.
Tak apa. Cuba sebab kalau saya nak pergi go through satu-satu lambatlah habis pukul 10 nanti.
Oi.
Banyak
Oi.
tak ada. Banyak exercises to help you, okay? So we not afford to go all of them. So okay, you already take the photo, that's all right? Okay. You nak share dalam group WhatsApp pun tak boleh juga gambar-gambar tadi tu. Okay. Okay. So then we continue with the power. When we discuss about voltage, we discuss about signal. The next concept we need to touch is the power lah. Power in amplitude modulation. So this is our sideband. Okay, this is lower sideband omega c minus omega m, and this is upper sideband. In the modulation process, signal is converted to electrical signal in terms of current or voltage. This one is normal is either current or voltage. Therefore, if we have either current or voltage, adalah power tu. Sebab power is a formula power is coming from the derivation of voltage or current. Okay. So this is your carrier signals components VC. This one is your VLSB lower sideband voltage or signals. This one. So this is the amplitude for the lower sideband, which is this one. And then this is the amplitude for the upper sideband. They are the same because they actually just divide by 2. Okay. And then you have EC. So because we are actually still under double sideband full carrier, mean we are transmitting, okay, double sideband full carrier, we are transmitting both sideband and carrier as well. So that's why in calculation of the power, we must consider all component, carrier component, lower sideband component, upper sideband component. So for the carrier component, it is a VC RMS square over 2 over I. So because this one is AC circuit, we cannot take the maximum value to calculate for power. We must take the RMS value. Okay. So VRMS, we expand it equals to EC over square root of 2. This one is the maximum value of the EC lah. Okay. Um, let's say 10 cos omega C, so it's 10 here, 10 over square root of 2. Similarly, for the sideband, the amplitude is MEC, right? MEC over 2. The amplitude of the sideband, MEC over 2. But because it is RMS value, you must divide by square root. That's why you have M. Okay, initially it was MEC over 2 divide by square root of 2. Then you do rearranging, you get MC over 2 square root of 2. And because all of them is square, okay, following this, So that's why we have square here. So that's why you have this thing. Okay. So similarly for upper sideband, and then because following the power original formula over R, so that's why you have over R. Normally, if we didn't mention, again I repeat, okay, like last time, if we didn't mention the value of R, you can assume R equals to 1. If we mention 50 ohm, 75, we have to use that. Okay. And after that, the expansion, you have this as the result. Okay. So EC square over 2R and so on. If you notice they are a bit similar, then we can do some more factorization. Okay. So PC is, this is the formula. Lower sideband sharing the same formula, uh, which is M square over EC square over 8R. Okay. So power sideband, since they are identical, you can combine them. Okay. You can combine them. So this one is PC equals to EC square over 2R. If you notice power, EC square over 2R. This is the sideband. So M square, EC square over 8R. If we do factorization with the PC being EC over square, so M square over 4, and you have EC square over 2R. Okay, EC square over 2R. Then it becomes M square over 4 PC. Okay, that's why you have this. Okay, and because they are similar, you can add up them together. So resulting in this one. Okay, just like 1 over 4 plus 1 over 4, you will get 1 over 2. Okay, so PC plus PSB for the total, you have PC plus M square PC is here over 2. Then you do factorization, you have PC, you take it out. So 1 plus M2 over 2. Okay, like that. As long as you understand one thing, the rest you can just extend or factorize. Okay. Konsep tu yang kena penting lah. Okay? Faham. So PT is the total power is equals to total power in amplitude modulation is equals to this. So transmission efficiency for N, okay, this one is eta. It's not N, it's eta. So N is eta equals to total power over power of the sideband. Okay, it's not power of the carrier because the one that having information is only sideband, not the carrier. Okay, so that's how it. So that's why our the upper part is our power that containing the information. Okay, times 100%. Where PSB is the total sideband signal that contain information. So we have eta. You expand again as what from the previous slide. In the end, you will have M square over 2 plus M square. Okay. Later on, I will share again you the appendix so you know what you need to memorize and what you did not need to memorize. Okay. If M is equals to 100% modulation, M equals to 1, the average power PSP equals to 50%. Okay. If M is equals to 1, okay. Uh, right. Okay. So if M is equals to 1, considering 100% modulation, okay. So let's say you put here 1 square, plus 2 plus 1. Okay, so this is the efficiency. Okay, transmission efficiency 1 over 3. Okay, so the average power PSB, okay, PSB power segment 50%. Okay, PC equals to PC over 2. This one is you just plug in the value. Okay, so PSB power of the segment, okay, is dependent on the value of M. Okay, remember this one is power efficiency, and power efficiency is derivation of PSB. So simple saying, it is actually they are dependent from each others. Okay, with uh with this all equation that you have lah. Okay, this one is in the appendix. If I'm not mistaken, this one I'm not sure, but pretty much even if it's not in the appendix, you can relate lah. Okay. So the transmission efficiency with M equals to 1 is only 33.3%. So this number just now, okay? So therefore we can conclude that the transmitted power signal is mostly carrier, 66.7%. That's why when you see in the power side, in the double sideband full carrier, okay, you see that carrier have the most magnitude, the most amplitude. And when you calculate for the power, actually for double sideband, full carrier, the carrier contribute to 60% of the power, whereas sideband is only contributing to around 33%. Okay, this one is around 37 lah. Okay, 37. Okay, so it is a wastage of power because power did not contain information. Okay? And then the information is only reside in the sideband, which each sideband have the same information. In practice, information signal is complex and non-periodic. Okay, like I told you, it's not only like course every time. It can be RAM, it can be straight, pass straight, it can be rectangular, and so on, and a lot more. So, but for simplicity, we just use course. Okay, and then all signals, like what we understand from chapter 1 just now, we have harmonics. Okay, so harmonics mean is a repetition of frequency. So let's say for music, video, images, we have many frequency and harmonic components. So for example, Vm equals to em1 cos omega m1, and then we have another harmonics is omega m2. Okay, so the problem having harmonics, we call it uh what is the name, multitone. Okay, where we have multiple harmonics. Okay, if anyone coming late and didn't scan attendance yet, please let me know, because I shared the attendance just now at 2 and 2:05 p.m. So maybe someone miss out the attendance form. If you miss out attendance form, just interrupt me. Okay. So for the multi-tone problems where we have a lot of harmonics, okay. So we have harmonics. For example, we have this is the same carrier. We have uh this M1, and then we have another. Okay, we say omega C now minus omega M2, and then M plus, and then we have omega C plus omega M2. Okay, so this situation we have two messages in a VM1 and VM2. Okay, so means they have two different value of M. So that's why we say have here M1, M2, M3, and so on. Depends on how many signals is present. Okay. Because it is a multi-tone problems, we can take into account the effective value of modulation index by using formula M effective equals to square root of M12 plus M2. If there is two message in it, if there is three, then it's three lah, and so on. Okay, so that's why they use here. So this one is square root of 2. Okay, and of course, like what you see, M1 is EM1 over EC. So this one is, because it's M2, EM2 over ECM. Okay, so this is the second, and this is the first, M, EM1 over EC. And of course, this one is just EC lah. Okay, next is also the summarize. So like what I told you in terms of power lah, because we are wasting, power is wasting around 16.67 because it's not we don't have any information. So this one is pretty much what I mentioned. Okay, and then let me end this show first by removing this one, the oh, tak boleh Sekejap okay, I want to remove this. Oh my god. Sekejap tukar color, shape view. Okay. So this one is better lah, but better for your view. Okay, you can take this and you can try it at home. Okay, so 10 kilowatt, when modulation percentage is 60%. So you just put 60% here, and then you get the answer lah. Okay, I think something is missing here. Okay, this one lah. Okay, so you can try it at home. Okay, next is the double sideband full suppressed carrier. Having that understanding just now from double sideband full carrier. Double sideband full carrier we have like this and carrier in the middle. So this is lower sideband. This one is upper sideband, and this one is carrier. So in double sideband suppressed carrier, we're going to suppress the carrier, so we don't send carrier. Okay. So to increase the transmitter efficiency, the carrier can be removed, can be suppressed from the M signal because it doesn't have any information. It's just wastage of power. So this produce a DSB SC. A suppressed carrier is amplitude. A suppressed carrier DSB SC is 3 times more power efficient than traditional DSB FCA because we only submit sideband, no carrier component at all. So VM, VCT, let's say VDSB FCA, from you understand this one is SC, FC equals to EC plus VM cos omega CT. Because in the double sideband suppressed carrier, EC is 0, means we suppress, so 0. So that's why you end up VM cos omega CT, with VM is actually EM cos omega MT. So this is the long-term answer lah. So this one will be VDSB SC. SC. Okay. So the same thing that I showed just now. Okay. Then from trigonometry, cos A and cos B taken into account, you will have this omega C plus omega M. Then you have omega C minus omega M. So you're going to have the lower sideband, and you're going to have upper sideband. with the amplitude becoming EM over 2. Okay. So this is to show how is actually your omega m is very far behind. Normally we don't plot this unless the question asks. Okay. Okay. Normally it's just like to show the others sideband and carrier component. Okay. Then this is omega, and this is your magnitude, as what we learned just now. And this is our lower sideband minus, and this is our sideband. With our carrier is being suppressed, there is no more for double sideband suppressed carrier. Then, having discussed power in double sideband full carrier, we also need to know power in double sideband suppressed carrier. Okay, power in double sideband suppressed carrier. So it's just similarly with the one that we learned in double sideband full carrier, it's just that there is no more P carrier. Okay. So AM DSPSC you get this the value, okay, and then to calculate for the power, PT with PC equals to 0 because we suppress the carrier. So we end up with VLSB RMS and VUSB RMS. So you end up just like what in the double sideband full carrier, but you only have the double sideband component. So EM square over 4R. In DSBSC, all the power transmitted is sideband power. Okay, logic because carriers no longer exist. If R is equals to 1 ohm, so the PT is equals to PSB. The total power is actually come from the sideband power if the R is equals to 1. Okay, this is just to show easy relation if we convert this R equals to 1. Okay, senang sikit nak nampak. Therefore, in terms of efficiency, in terms of transmission efficiency of information, it is 100% because we sending all signals containing information. We don't send them together with carrier. Okay, means we don't have solely carrier component. Okay, we just have upper sideband and lower sideband. So both of them contain information. That's why transmission efficiency is 100%. Okay. Next is single sideband full suppressed carrier, where we have double sideband initially. Okay, we have double sideband suppressed carrier. Now we only want one of them and remove the other one. So let's say this one we want one of them is lower sideband, so we only have single sideband suppressed carrier LSB, for example, lower sideband. Okay, so by having this single sideband, we reduce the power or bandwidth even more because we only send one signals. We send only one sideband instead of two. Okay, so both in the double sideband full carrier and double sideband suppressed carrier having larger bandwidth twice compared to single sideband full carrier, because if for the case of double sideband full carrier, even though we have the carrier and the sideband, this one is still 2 omega m, okay, the bandwidth. And then if we have double sideband suppressed carrier, so we still have 2 omega m, even though carrier is already removed because it's still required the bandwidth of 2 omega m. So in single sideband suppressed carrier, okay, we only have half of the bandwidth. Let's say we have single sideband suppressed carrier at lower sideband, so our bandwidth is only this omega m. Okay, so it's half of the bandwidth of these two. Okay, so that's why AM single sideband suppressed carrier is even better version to reduce the power. Okay, so the modulation VMT, our modulating signals, mixed with our carrier, go through modulator of single sideband, then you're going to have EC plus VMT cos omega CT. Okay. The next slide hopefully will show you better understanding. Okay. So let's say you have a VM equals to EM cos omega MT. Okay. This one is your message signal. And then you have VH. Let's say you have VH cos omega MCT minus pi over 2. Okay. AM SSB, AM SSB single sideband. Okay. You can have EM cos omega C. Wait, I want to show you how. Okay, here. Okay, so I want to show it to you first. For example, okay, I think some of you maybe already know. Okay, cos and sine can be related by lambda over 2. By lambda over 2, 90 degree. So this one is trying to show by having cos, for example, theta divided by 90 degree. Okay, because lambda over 2 is equals to the theta. Okay, this one you can test yourself at home. Okay, let's say cos 130 minus 90, you will get it is actually equals to sine 90. Okay, but to cut it short, I just show you some ideas. Okay, so later you can try at home. Okay, EM cos omega M, this is your modulating signal. This one is your VHT. Okay, it's actually just multiply with each other. VM and VH, and then you have EM over 2 cos omega MT and cos omega CT plus minus. Okay, plus minus. Sin omega M, sin omega T. Okay, so from the trigonometry, okay, because you see here, this one is cos A, cos B. This one is sin A, sin B. Okay, from cos A, cos B, from cos A, cos B, you will have half cos A minus B plus half cos A plus B. Okay. From sin A, sin B, you have half cos A minus B minus half cos A plus B. Okay. Then AM, ASB, AM single sideband suppressed carrier equals to EM over 4 because this one is, if you notice, this one is divided by 2, right? But because this one is cos A, cos B is another divided by 2, that's why when you combine and when you expand, it will be over 4. This is how you get the over 4. Okay. Then EM, maybe I use different colors so easy on your eyes to distinguish them. Okay. So EM cos omega MC. Okay, over 4. Omega C minus omega M plus EM over 4 cos omega C plus omega M. And this is plus minus. So this will determine what sideband we want, whether it is upper sideband or lower sideband. Let's say we choose this one to be plus. Okay, let's say we choose this one to be plus. Okay. So EM cos omega C minus omega M plus EM over cos omega C omega M. Okay. So let's say this one is plus EM cos omega C plus omega M plus EM over 4. So you're going to have half because it's 1 over 4 plus over 4. So you have half EM cos omega C minus omega M T. But for this, EM over 4, if you notice EM over 4 plus plus minus. Okay, so that's why it's become 0. So for this situation, if it's plus, we are sending only lower sideband. Okay, and the process will be terbalik if we choose negative here, minus. So we will submit instead upper sideband. Okay. Okay, so I have explained the slide, just show it better. Okay. So for single sideband suppressed carrier, do not mistaken because this already happened to our Perdana student, for our to our mainstream student. We are asking single sideband suppressed carrier, but the way they draw is look like double sideband full carrier like this. It is wrong. Remember, uh, for single sideband suppressed carrier, we did not send the FC component. Okay, we did not send the carrier component. That's why we don't have this shape. Instead, we're going to have this kind of shape. So if it's omega C minus omega M means lower sideband. So that's why you see it is lower frequency compared to this one. This one is if you send omega C plus omega M, it is higher frequency in terms of more padat. This one is more compressed. The shape look like more compressed. Means we have more complete cycle over time. This one is we have like extend a bit. It have low. It means it have lower completed cycle in a unit of time. Okay. So this is one is lower frequency. This one if we submit upper frequency or upper sideband. Okay. So in terms of power, in the single sideband suppressed carrier, okay. So in terms of power, EM over 2, EM over 2, okay. In terms of the amplitude, that will be calculated as power, okay. So this one is amplitude, okay. V or amplitude V. So this is EM over 2, not yet power, but when you calculate power, you need to consider RMS, okay. Then this is the make sure also this one label properly, okay. Sometimes the perdana student lose mark because they don't answer is already wrong, but at the same time they didn't label, maki hilang markah dia. Okay. So power sideband in power of amplitude modulation in single sideband suppressed carrier. So our power is made up by this component. Okay. So in power sideband, single sideband suppressed carrier, because you only send one of the sideband, so that's why our total power is either contributed by lower sideband or upper sideband, but not both because it's single sideband. So that's why in the end you will still have EM square over 4 at R. If we submitted double sideband, it will be EM square over 4R. We therefore reduce the transmitting power by 50% compared to double sideband suppressed carrier. Okay, because a double sideband suppressed carrier sending two spectrum, sending two sideband, but single sideband only send one. So it's 50% more reduced in terms of power. Okay, but the transmitter efficiency is still 100%. Why? Because we are still sending spectrum that containing the information. Double sideband suppressed carrier is still 100% efficiency because still submitting power as submitting information. So vertical sideband, okay, is a sideband. This one is not really famous kind of question, but it has been asked. Okay, it has been asked before, even though look not famous, because this one is only 2 slide, if I'm not mistaken. Yes, only 2 slide, but uh last time is being asked, it ended up as text question of an exam. Okay, vestigial, even though two slides. So what happened is actually for the vestigial sideband is that we submit single sideband suppressed carrier. Let's say we submit on the lower sideband, but but for vestigial sideband, we will still stand that sideband, but with some portion of the other band. Okay. For example, this one is your lower sideband. Okay. And then you only send one band. Okay. So you have upper sideband initially. Okay. But the concept of vestigial sideband is that you take a portion all the range, okay, at the lower sideband with some, not all, with some of the range in the upper sideband. Okay. So vertical sideband is actually is more practical in a way on the system lah. We cannot have sharp. We have gradual. Okay. VSP combine the advantage of both previous scheme. It's easier to generate the bandwidth of SAV approximately 20% more than SSV. In VSP, instead of rejecting one sideband collectively, a gradual cutoff of one sideband takes place. So gradual, not all. Okay, but let's say if one just submit LSP, we take a portion of our upper sideband. So that's why you have this lah. Okay. So a special bandpass filter having transfer function of is used to suppress one sideband gradually and give the signal a particular shape. Less expensive than single sideband suppressed carrier. Okay. And it is using lower order filter. I think in senior system you have learned some of the filter lah. Okay. Mm, that is how is it lah. Okay. Filter is we take frequency that we want, and the frequency that we want we rejected them out. Okay. So this one is at the transmitter side, and this one is at the this one is the resultant of the VSB of signals. Okay. Not double sideband full carrier, not double sideband suppressed carrier, not single sideband suppressed carrier. Is a single sideband. Okay. So this one I assume not so much importance. Okay. Mm, the question last time on this chapter is on this vertical sideband interpreters is more like maybe illustration. Okay. We don't ask you to do equation for vertical sideband. Okay. And then we have after we finish on the parts of uh ge- of spectrum and whatnot, okay, in general, then the next is we will learn about generation. Okay. Generation and risk detection. Okay. Mostly will be asked. Mostly means not totally absent in test. Mostly we will ask the question that require design, like how to design SSBSC, how to design FM, whatever. That one will keep as a final exam question. Means final exam question will cater on the design part, and then test one and test two just normal. Okay, I will share to you the test one and test two later on. Okay, so that you understand. Now, in order for us to produce a double sideband full carrier, okay, there are two methods, which is the we call it direct and indirect method. Normally, indirect method is more challenging. Okay, indirect method is more challenging because you will learn the method direct, indirect to produce double sideband full carrier, to produce single sideband suppressed carrier, and so on. Okay, so you have this as a direct signal. So you have message signal with VMT. Then you have balance modulator that will perform modulation. Okay, for the direct method. For the direct method, we will introduce our carrier. Okay, of course magnitude of one, but it can be magnitude of two. No problem. It's just that you need to be aware. This one below is VC. Okay. So it's cos omega C. And then what happened after that? is 1, then it will be multiplied by EC to the value that we want. Okay. So let's say EC here is 1, right? But after going to amplify, we want it 10 VC. So 10 cos omega C because it's being amplified by 10. Okay. And then from there, we have EC cos omega C going to the mixer. Okay. So settle there. For the basic signal going to balance modulator, you will end up having single sideband suppressed equation. Okay. Whether uh, upper sideband, sorry, you have the equation of the carrier component together with the VMT. Because this one is DSBFC, okay, it must produce, okay, so which is this? Multiplier can be expensive and complex. Okay, so multiplier, good to know for now. Okay. I'm not sure why it's there. Okay, good for now. The word multiplier and this one. Good for you that some of you have class or whatever. This one we can go through in different in different chapters, okay? Because this one is multipliers is in the different class, okay? In the different class is FM, okay? But in here, just enough for you to understand the EC will be multiplied by EC1 is multiplied by the amplifier lah, to become whatever value that we want for the EC. Okay, because end up they will be added up. Okay, for example, this one is VM T cos omega CT plus this one 10 cos. Then you do factorization plus this one plus. That's why you have 10 VMT plus MT cos omega CT. Okay, so this one is DSB FC. Okay, so indirect method is more challenging. Indirect method has been asked. Kejap dah tanya I need to check forget already. We have asked a bit challenging question in the mainstream about the detection on the double sideband full carrier. Maybe we go through that later lah. Okay. I think not indirect, but the other parts. Okay. Okay, but still in detection at double sideband full carrier. Okay. So for the indirect method, we require the use of non-linear device. Okay. Non-linear devices we have a lot. Again, for example, transistors. Okay. But for now, you don't have to know what it is, what inside. You don't have to know. Okay. Also for this, you don't have to know. It's just a block diagram. What you should understand and what you. If the question asks you, maybe just do block diagram in equation, but we don't ask you to. We don't to ask ask you what is inside of that. Okay. So VMT and VCT, they are in parallel. They are in series together. They are actually VI. VI equals to VM plus VC. Okay, going through the non-linear device. Okay, so this is as your input signal, and then output of the non-linear device. Okay, you're going to have as the VK. Okay, so it's E0 plus M1 V1, M2 Vi2, M3 Vi3. If you have 4, M4 Vi4, and so on. Okay. So again, no need to see what inside. Just understand this will do. Okay. What happens is that we will have from this non-linear device, we will have a lot of harmonics. Okay. So that's why we will use this band pass filter to limit to the frequency range that we want. Okay. So let's say we want lower component, lower frequency component. So we will okay, we will remove the other component. So you see here, VK signal was the filter using bandpass filter tuned at the resonant frequency FO equals to FC. Okay, so we don't want the harmonics. Okay, so you have here bandpass filter at the lower at resonant frequency omega C. Okay, so this one will be filtered out. All of this because it's continuous. Okay, will be filtered out, and then end up we only take. Okay, we only have this is our output EC cos omega C, omega 2 EM2 EC, and so on. So we only take until, for example, until M2. Okay, until second. Okay, so depending on the question. Okay, so bandpass filter is for us to remove the frequency that we did not want. Okay. So compare the output of the signals, VAM. Okay, this one is the initial formula that you understand, the DSPFC, and then the output from the from indirect method. Sorry, from indirect method. You can compare. It is almost like uh, similar. Okay, the output is similar because the frequency component are similar even though with different amplitude. Okay, almost look similar. Okay. Frequency spectrum before bandpass filter before and frequency spectrum after bandpass filter. You will see that with the bandpass filter, we will remove the frequency that we don't want, okay, and only maintain the frequency range that we want, even though it is with noise. So that's why this is your bandpass frequency. Maybe it's around FB, for example, and this one is maybe minus FB. Okay, well, FB is actually great. Well, FB is actually greater than FC plus FF, greater but lower than but FS, but FB is lesser than 2FC. Okay, here because it's only covered the frequency that we want. Okay, so next part is actually a double sideband suppressed carrier. Okay, double sideband suppressed carrier generation. Okay, so there is again two. If I'm not mistaken, there is two direct and indirect. Okay, so direct is we just repeat again. We just use balance modulator, just like what we use in double sideband full carrier. We use balance modulator. Okay, then function like multiplier generates only lower sideband and USB signal upper sideband. So you have original signals. Okay, and then you have VC as the carrier component. Mix them up, you're going to have double sideband suppressed carrier. Okay, VM cos omega CT. Okay, so VM here we can tambah lagi kan. If we have, let's say, cos omega MT, cos omega CT. So this will trigger the trigonometry lah, because this one is cos A, cos B. Okay, so this is your message signal, this is your carrier signal, and this is double sideband suppressed carrier. Okay, modulated signal. So double sideband full carrier is like this. Double sideband suppressed carrier is like this. And then single sideband suppressed carrier, you only have the normal cos. Okay, because we don't have carrier component. Okay. Next is the mathematic analysis for Fourier series, okay, the carrier signal VC is given by, okay, I think you learn Fourier series in chapter 2 of signal and system, okay. Okay, so I think you pretty much know what this. So sin omega c 1 over 3. So it will have another 1 over 5, for example, sin omega 5 omega c t. Okay. Okay, so if Vmt equals to Em cos omega mt and k is multiplier, okay, multiplier sensitivity factor, please highlight this, okay. Modulator can be expressed as V output, okay, output from the modulator equals to k Vm dot Vc, okay. K is constant, Em you just extend it from your understanding, and Vc is you take from here, okay. Question maybe give you, depend, okay. And then you will have this answer and this answer with extension. We have a lot more answer, which we couldn't we are not advised to write all of them because otherwise it take your time. We just want anti-frequency that we want. Okay. Okay. So for KE and so on, this one is just for the sake of expansion. Then you have upper sideband and lower sidebands. Okay. The modulator output depends on which one. Okay. That you want. Okay. Or the question one. The next is double sideband suppressed carrier indirect method. Okay, this question has been asked in the final exam. Okay, mm, I'm not sure. Maybe I'm the one making that question. Okay, it has been asked in the final exam. For the previous batch. Okay, so for double sideband suppressed carrier, it will use two full AM modulators. The input signals are the same with different polarity. So there is plus, there is minus. Okay. And then it will use the same carrier frequency. Okay. So imagining we have half VMT. This one is not always half. Again, I would like to mention this one is not always half. Okay. Do not take it half, but the outcome of this you should have a clean. Okay, you should have a clean. For example, half plus half, you will end up if having it as one. So this way you have Vm cos omega c. They say you have what else you have? They say this one is 1/10 and the other is 1/10. Okay, so you're going to have what there? Okay, remember this one, this value is not always half, is going to change the value here. Okay, so half BMT going to full modulator mixed with EC cos omega ct, you're going to have double sideband full carrier equation with reduced magnitude of message signal. Okay, so this is the positive polarity. Okay, remember the word here, polarity. And the other is being assigned a negative polarity. Okay, going through again the same process, EC cos omega ct mixed with half negative half EMT, you're going to have minus. However, if you notice, this one is EC, right? EC plus minus EC, this one, combine with this one, right? EC plus minus, because it's minus EC. So what happened is that this one is hilang lah. Okay, because EC minus EC. Then we have half VM, we take into this one, and then half here minus, okay, minus, because it's minus here, and then minus, okay, minus the minus half, plus half, minus negative half. So that's why you get just VMT. Okay. Okay, we rest 5 minutes. Okay. I need to take some udara sekejap. Okay, 5 minutes. No, udara lah, bernafas nak rehat jap. Okay. So okay, record 5 minutes. We will continue 3:15